Hello everyone, welcome back to the course on cryptography and network security. In today's session, we'll be discussing on symmetric cipher. In today's session, we'll be discussing on the introduction to symmetric cipher, types of symmetric ciphers, block cipher versus stream cipher, Feistel cipher structure, and the overview of SDS algorithm and the key generation process. From this session, my students will be able to define symmetric cryptography and explain its importance in secure communication, and they can able to differentiate between block ciphers and the stream cipher based on the working principle, advantages, and the use cases. Explain this Feistel cipher structure and its role in modern encryption algorithms, and also they will be able to illustrate the working of SDS algorithm by step-by-step transformations, and also they are able to demonstrate SDS key generation using the permutation and shifting techniques. Before getting into the symmetric key cryptography, we try to understand what is basically cryptography is. Cryptography ensures in the communication confidentiality, integrity, and authentication. So we have two types of cryptography techniques. The one is symmetric key cryptography, the another one is asymmetric key cryptography. So in the case of symmetric key cryptography, we are going to be using the common key between the users in order to perform the encryption and decryption of their messages before putting into the communication channel. And in the case of asymmetric key cryptography, they're going to be using two different keys, one for encryption and another one for decryption. We will discuss asymmetric key cryptography in the next coming sessions. So in this session, we are mainly concentrating on symmetric key cryptography. What do you mean by symmetric key cipher? Uses the same key for encryption and decryption. So it is going to be performing very fast and efficient algorithms we can able to see in the case of symmetric key. So it is best suitable for bulk data transcription, encryption, and it is going to be using a single shared key and high speed in terms of performing encryption, and the less computational overhead will be there in terms of implementing with respect to the hardware. And the main challenge in this particular technique is the key distribution. The common secret key we are using for encryption and decryption, the sharing of that key will be more challenging in this particular technique. So now we need to understand, when we go for symmetric or asymmetric and all, the messages which we are going to be encrypting in terms of block or in terms of stream. So the plain text is going to be get converted into ciphertext, so in the form of block or in the form of stream. So now we understand, so what is basically the block cipher versus stream cipher. Block cipher, a block of plain text, is treated as a whole and use it to produce the ciphertext block of equal length. So typically in the case of block ciphers, the size varies from 64-bit to 128 bits. So where we can able to make use of this block cipher, so especially in the case of data encryption standard, in short we call it as DES algorithm, where each message block is of size 64-bit. And in the case of advanced encryption standard, in short AES algorithm, the message block size will be 128-bit. So in the case of stream cipher, so it is going to be processing the entire messages in the form of bit or in the form of byte at a time. So the example where we are going to be using the stream cipher are auto-keyed Visioner cipher and the Burnham cipher. So here is the block diagram. We can able to understand how the block ciphers will be get generated and how the stream cipher is going to be working. So in the case of very first block So bit stream generation algorithm. So the messages we are going to be using, so bit in the form of bits continuously. So here in the left hand side, I will be go on sending the bits of the given plain text to the encryption algorithm, and the key which we are going to be using in the form of bits. So both the bits is going to be performing the XOR operations. So and it produces the ciphertext. And the ciphertext bit patterns you are sending as an input to the decryption algorithm, and the same key we are going to be using it, and the output will become in the form of bit patterns that we call as a stream of cipher. When it comes to block cipher, so here what we are going to be seeing a plain text of size b bits. So whatever may be the length of the messages, the entire message will be get divided into equal size blocks, and every block will undergo encryption algorithm with a specific key that is going to be producing the ciphertext. So similarly, it will be go on process for all the blocks of the messages from plain text to ciphertext. So that is we call it as block cipher. So now we need to understand what is basically the Feistel cipher. So Feistel proposed the use of cipher that alternates the substitution and permutation. So in the case of symmetric encryption algorithms and all, we will be basically use the substitution method and the permutation method. So each plain text element or a group of element is uniquely replaced by a corresponding ciphertext elements or a group of elements. That is we call it as substitution. And a sequence of plain text elements is replaced by a permutation of that sequence called as permutation. So this is a practical application proposed by Claude Shannon to develop a product cipher that alternates confusion and diffusion functions. So here is the one structure we can able to understand how the entire message of 64-bit will undergo the encryption process to produce a 64-bit of block cipher text. So here, so we have a number of rounds. So in the case of Feistel cipher structure, basically the structure we are adopted in DES algorithm. The DES algorithm is going to be performed 16 rounds of operations. So in every round, when we go for converting a block of plain text into a block of ciphertext, so these are the rounds it has to undergo. In every round, before that, so that input whatever with the size, the 64-bit, that will be get divided into two equal halves, the left side and the right side one. So the right side one is giving as an input to the function. So that function, it takes the key, and whatever the output of that given function will come, that will be give it as to the left side, and the left side part of the initial block is giving to the input to the XOR function. The output of the function f and the left hand half is performing the XOR. So and the output we are going to be considered as the right side half. So when we combine 32-bit plus 32-bit, so that becomes an input to the next round. So likewise in every round, so it will be go on process. So after the 16 rounds of the operation, we just swapping the left side half and the right side half in order to get back our very first cipher block text in the form of 64 bits. So at the same time, when we go for performing the decryption, the same Feistel cipher structure we are going to be using to perform the decryption process. The output, what we got in the encryption process, that will become an input to the decryption one, the left hand side and the right hand side. So I'm going to be passing. So the swap, whatever the values are there, I'm going to be passing into the function f with the key value, and the same thing which is going to be passing into the left side for the next round, and the left side will be go on performing with the XOR operation. We are going to be get the right side value. So likewise, the 16 rounds of process will undergo in order to get back my original plain text. So how many blocks are there in the given messages? every block is going to be undergoes a 16 rounds of operation, so either in the encryption process or in the decryption process. So now we need to be understand, so how exactly the data encryption standard. So data encryption standard algorithm is going to be work with respect to 64-bit of key and the 64-bit of plain text. So when we go for performing or understanding the working of DES algorithm, so first we try to understand how a simplified DES algorithm is going to be process of converting a plain text into ciphertext. So simplified data encryption standard has been developed in the year 1996 as a teaching tool. So in order to understand the data encryption standard original algorithm, so they have been proposed this SDS as a teaching tool. So Santa Clara University, the professor Edward Cipher, so he has been proposed as a teaching tool to understand the DES algorithm. So it is going to be taking an 8-bit of block plain text and 10-bit of key, so that is going to be produces an 8-bit block of ciphertext. So instead of taking 64-bit of plain text and the 64-bit of key, so we try to understanding by considering 8-bit plain text and the 10-bit key, so in order to get 8-bit block of ciphertext. So decryption also will be gone takes place the 8-bit block of ciphertext and the same key we are going to be using to produce original 8-bit block of plain text. So this is basically the scheme of SDS algorithm. So here is the key we are going to be using. So we are going to be specifically use a key generation algorithm in the SDS. So whatever the 10-bit key is here, so that is recorded as a 10-bit, that I'll be gone performing the left shift operation. So whatever the 10 bits are, the original key is there, I'll be performing the very first left shift by 1 bit. I'll be perform from that set of bits, I'll be go on permuting the 8 bits. So the very first 8 bits what I'm going to be getting, so that I'm going to be considered as K1. And so whatever the output of the left shift operation by 1 bit, we have done the same thing which we are going to be doing one more time towards the left side. So from that I'll be going selecting one more 8-bit values, so that I'm going to be considered as K2. So in the case of SDS scheme, we are going to be deriving 2 sub keys from the original 10-bit key. So both the keys are of size 8 bits, because our plain text block is of size 8 bits. In order to perform the operations, we are going to be using the 8-bit keys out of 10-bit. So now once we derive the key, 2 sub keys for processing the SDS scheme, so now we enter into the encryption mechanism. So whatever the 8-bit plain text is there, I'll be go on perform the very first step is initial permutation. So after the initial permutation, I'll be passing those bits into the function fk. So in that function, I'll be go on considering the k1 to perform the operation with the 8-bit plain text. So the output of that given function, I'll be go on performing the swapping. So once I've done the swapping of 2 equal halves, then again I'll be go on give it to the function fk with the sub key k2. So the output of the given function fk in the second round, so I'll be just go on performing inverse initial permutation. So then output of that will be considered as 8-bit ciphertext. So this is basically the steps which is involved in the case of SDS algorithm. So now when it comes to 8-bit plain text decryption, that is ciphertext. So 8-bit ciphertext, again I'll be gone performing with the initial permutation, then I'll be passing into the function fk with k2, and then I'll perform the swapping, the output of the given function. Then those values will be sending into as an input to the next round of function fk with the sub key k1, the output what I'm going to be getting. So I'll be gone performing the inverse initial permutation, so that I'll be able to get back my 8-bit plain text. So in the same fashion, so in the DES algorithm, the original DES algorithm is going to be executes. So this is the encryption process, how basically we'll be gone performing it. So from the initial permutation, so I'll be gone passing into the function f with the k1 value. Then output of that function, I'll be performing the swapping. So after swapping, the values will be given as an input to the fk2, the function k with the sub key2, and the output of that I'll be going getting into initial permutation. So this is basically we are going to be performing with respect to encryption. The same thing which we have mentioned here, ciphertext. The plain text performs the initial permutation. That output I'm giving it to the function f with the k1 values. Then output of that I'll performing the swapping operation. From the swapping is giving us an input to the next round of the function f with k2 value. That output I'll be going get back with the inverse initial permutation. So when we go for deriving the k1, so whatever the 10 bit of key is there, first I'll perform the left shift by 1 bit. From that set of 10 bits, I'm selecting 8 bits by making use of permutation. Then the second key, I'll be going deriving output from the k1. I'll be performing one more time the 8 shift, that left shift operation by 1 bit. From that I'll be going permuting 8 bits. So how I'll be able to get back my plain text is, so ciphertext initial permutation, from that passing into the function f with the k2 value, swapping. The output of that I'm giving it to the function f with the k1 value. At last I'll be gone performing inverse initial permutation. So this is the steps which is involved in the case of SDS encryption. So as I told, the key generation, SDS key generation, so 10 bit key, so I'll perform the permutation 10 bit, then I'll be divided into 2 equal half, 5 bit plus 5 bit. So I'll be gone performing the left shift by 1 bit. Then so output of this left shift operation, I'll be gone selecting only the 8 bits. That 8 bit I'm going to be considered as k1. And so whatever we have done the left shift operation by 1 bit, so that I'm going to be performing one more time the left shift operation. From that output I will be gone selecting so the permutation of 8 bits, so those values will become an k2. So this is how the key generation algorithm is going to be deriving 2 sub keys from the original 10 bit of key. So we try to understand what are the various advantages and the limitation of the symmetric cipher. So advantages, it performs the fast encryption, efficient for the large data, and the computational cost will be lesser. And when it comes to the limitations, key distribution problem, scalability issues, and the less secure than asymmetric. So because keeping key secret is more challenging, so that is we call it as less secure than asymmetric. So at this juncture, so we are going to be summarizing that symmetric ciphers are going to be using a single keys, and we understand so what is basically called block cipher versus stream, and then how the Feistel structure is fundamental use for DS or the symmetric algorithms and all, and also we understand ESDS demonstrate the real cipher designs. So with this note, so we are going to be ending the today's session. So we will be come back with how to solve the problems on SDS key generation and SDS algorithm in the coming session. Thank you.